Let's look at acid strength and its relationship to molecular structure. You may have wondered, why do some hydrogen-containing molecules act as acids and others don't? H2S is an acid, but CH4 is not an acid. I'm like, yeah, well, the hydrogens are after the carbon. But why? I mean, we could write it H4C. Shouldn't that be an acid also? Why isn't it? Well, look at that. Why are some strong and others weak? Why is HCl a strong acid and HF is weak? I said, well, we can think of it as F being the little sister, and so she's a weak acid instead of a strong acid, but that's just me, personifying atoms, right? That's not a reason. Why? Okay, let's look at the binary acids first. So, binary acid, you've got a hydrogen and you've got another element, a nonmetal, something like Cl or F. What we want to do is we want to look at the bond between the hydrogen and the other element. Because to act as an acid, this hydrogen must be donated as a proton, meaning the hydrogen leaves and both of those electrons stay behind. So two things are going to affect this, the acidity, whether this is lost or not. The bond polarity and the bond strength. So to be acidic, the bond has to be polarized in the correct direction. We need to have the positive end of this dipole on the hydrogen and the negative end on the other element. So if we look at the bond between hydrogen and lithium, that would be a polar bond, but lithium would be the positive end and hydrogen is going to be the negative end. That's not favorable for losing hydrogen as a positive ion. Do you remember how we tell which way the dipole goes? Electronegativity, right? So several of you had me for Chem 1A, and it's not going to hurt you to hear this again because my guess is you don't quite remember it, and others of you didn't. So there's a table that gives all the electronegativity values for all the elements, and you can go look that up and do the subtraction and find out the dipole and all of that good stuff. That's great, but what we need to be able to do is to look at any given bond and be able to predict, is it polar? Which end is negative? And we can do that without a table. So on the periodic table, fluorine is the most electronegative element. And this is not always true, but it's true enough times that we don't need to mess with the rest of it. Whichever element is closer to fluorine is going to be more electronegative. Okay? If you have two identical atoms, like if you have hydrogen and hydrogen, of course that's going to be a nonpolar bond because you have to have a difference in electronegativity here of more than 0.4 in order for this to be considered a polar bond. Well, so if you have two nonmetals, like hydrogen and carbon, hydrogen and fluorine, I would expect you to tell me that that's a polar bond. There are exceptions, okay? The only exception that you need to remember is hydrogen and carbon. Hydrogen and carbon differ in electronegativity by 0.4, which is right on the borderline of polar and nonpolar. And so hydrogen-carbon bonds are always nonpolar. Why do we care about this particular one? Because it happens so much. Organic chemistry is full of carbon-hydrogen bonds. They are all nonpolar. So when we look at HC, this is a nonpolar bond, so the hydrogen is not at the positive end of a dipole. That cannot be acidic. Does that make sense? Here we have H and F. So the arrow is pointing to the one that's more acidic. More electronegative, right? More electronegative. And so my analogy was like two neighbors, And at the one house, they have a swimming pool and all these great things, the big Jumbotron TV and all the channels. The house next door, they have some grass in the backyard. They have an old black and white TV and a VHS player. Do you guys even know what those are? But just, real basic. Mom's very nice at everything, but they just don't have all the fun stuff. So there's a little boy that lives in each house. And where are they when they play together, where are they going to play? They're going to play at the house with all the cool stuff, right? So that's Florine's house. And this arrow is like, someone comes to the house and it's like, well, where's little Johnny? Where are the boys playing? And Dad goes, and he points at the more electronegative one. That's where the boys are. That's where they're having more fun. Okay? So here we're pointing to fluorine. This is going to be the negative end where the electrons spend more time. Remember, a polar bond, we have shared electrons, but they're not shared equally. They spend more time close to fluorine and less time close to hydrogen, and as a result, this end is a little bit positive and that end is a little bit negative. Any questions? Do you remember hearing about stuff like that? So we have to have it polarized in the correct direction. And then the stronger that bond is, the weaker the acid will be. So this is one of those things where we've got opposites, stronger, weaker, right? If the hydrogen is held by a strong bond, if it's held very tightly, it's less likely to come off, right? It's less likely to be lost. So the bond energies here are going to be a function of the size of the atoms. Fluorine is very small. Hydrogen and fluorine can get very close together. This bond is going to be short. Short bonds are strong bonds. Chlorine is bigger. Now, the distance between the nuclei has to get larger because chlorine's kind of bulky. And then we go to bromine, and bromine's even bigger. Bromine should maybe consider what he's eating. Diet change, maybe. And so bromine and hydrogen are further apart. The bond is weaker. Does that make sense? So if you're pulling hydrogens off of somebody, which one's easier to pull off? The weakly held one, right? I also have an analogy with family size. This is like, a family with one kid and maybe 3 kids and 4 kids, and then Iodine's down here with 6 kids like I have. And, if you're, I have some very politically incorrect analogies. So if you're trying to kidnap a child, right? Are you gonna go to the place where there's 2 parents and 1 kid, or 2 parents and 6 kids? The 6 kids, right? Because they might not even notice for a while, right? We left one of ours at church on Christmas Eve. We noticed within about 10 minutes, but you get the idea? So not politically correct, but maybe it helps you remember. So here, fluorine's holding on really tightly because it's small. So it's hard to remove this. And so that's why fluorine, hydrogen fluoride, is weak. Hydrochloric acid, hydrobromic acid are strong because that proton can be removed easily. So on the periodic table, if we look at, here's the elements F, HCl, Bri, and we put H's in front of them, and here we're making acids with those guys. As we go to the right, the electronegativity is increasing, which means that bond is more polarized. So HF is a stronger acid than H2O. When we're going down the periodic table, the bond strength is getting weaker because the family's getting bigger. It's harder to hold on to that hydrogen ion. So then things get stronger. Any questions? Remembering this is not a huge deal. I will not ask you to explain this on an exam, partly because I don't want to have to read your explanations and decide whether it gets full credit or not. That's just the fact. So I will not ask you to write an essay about that. But you might have a question on an exam that, gives you two acids and asks you which one's stronger. They're both weak acids. Well, which one's stronger?
You will not give us the bond energy.
Pardon me?
You will not give us the bond energy.
I won't give you the bond energy, no. Okay, so that was binary acids, and then there's oxyacids. Oxyacids have oxygen in there. In an oxyacid, the hydrogen is bonded to one of the oxygens. And then we have this other element, could be chlorine or nitrogen or whatever. So this other element may or may not have other bonds to it. It could have other oxygens here. Right now we're just looking at this structure here. So if Y, because what matters here is the strength of this bond between hydrogen and oxygen. Hydrogen-oxygen bond is a polar bond, right? Then we look at this guy, Y, and Y, if this is electronegative, Y will be pulling electrons from oxygen, which makes oxygen pull electrons from hydrogen even more. So the more electronegative this element is, the weaker this bond is and the stronger the acid. So if we compare these three, hypochlorous, hypobromous, hypoiodous acids, okay, we're looking, what's affecting the strength of this bond. Well, it's hydrogen-oxygen for all of them, but then let's look at who's next to the oxygen. Iodine, bromine, or chlorine. Chlorine has more electronegativity. It's 3.0. And so chlorine is going to pull electrons away from oxygen, which makes oxygen pull electrons away from hydrogen even more. So this is the most weakly held hydrogen, so this will be the strongest of the acids. So here, this one's 10 to the minus 8, 10 to the minus 9, 10 to the minus 11. Iodine is less electronegative than bromine. Any questions? Yeah.
I don't know. I don't get that.
You don't get the idea?
No.
Well, I'm sure several other people don't get it either, so thank you for asking. So we're accustomed to thinking of these two electrons as being shared between hydrogen and oxygen, and they're kind of in their own little world. And these two are being shared here, and it's just kind of independent of everything around it. Well, it's not independent. If you remember molecular orbital theory, electrons can be spread out over the entire molecule, and so what's going on over here does affect what's going on over there. So if this is more electronegative, it pulls the electrons away from oxygen. Oxygen was already pulling electrons away from hydrogen, and now Y is kind of helping it pull them away. So they get pulled away even more. Does that make sense?
Yeah, so I'm looking which one is more acidic.
The one that's more electronegative is more acidic, a stronger acid, which means that the Ka is larger. Anybody else have questions about that? Yeah.
So if the bond between the H and the O is weaker, that means that it's going to break.
Easier. Mm-hmm. Yeah, so, you could remember weaker, stronger, but good luck with that. I think it's better to remember we're looking at how strong or how weak is this bond. If this bond is weak, it's very easy for the hydrogen to come off. Well, if the hydrogen comes off easily, it's going to do that more. It's going to be a stronger acid. It's kind of you can't just have the one thing. You kind of have to go through this little conversation in your head. So the electronegativity of that element Y affects the acidity, and the number of oxygen atoms bonded to Y also affects it. So here we're looking at this family of oxyacids. This is chlorate, perchloric acid, hypochlorous acid, and hypochlorous acid. So they've all got this one ionizable hydrogen. It's on an oxygen. The next element over is chlorine for everything. So we're not looking at any electronegativity difference here, but this chlorine has more oxygens bonded to it. So oxygen is electronegative, and so it's going to be pulling on electrons. It's not very different from chlorine, but it's going to help pull electrons. So now we've got these three oxygens helping chlorine pull electrons away from that oxygen. Does that kind of make sense? So that makes this bond weaker. And in fact, it's so weak that this is a strong acid. That hydrogen always comes off in water. If there are two oxygens helping pull, it's not as strong. This has a Ka of 1, which means that at equilibrium you're going to have an equal concentration of HClO3 and ClO3 minus. So kind of close to a strong acid, but not strong. If we have one oxygen helping the chlorine pull things away, it gets weaker, and when we only have the chlorine and nobody helping, then it's very weak. So these oxygens, it's all about a tug of war for the electrons. So if we pull electrons away from this hydrogen, it makes it much easier for it to leave, and the acid will be stronger. Yeah. Well, this bond will be weak, but the acid will be strong. And I know that's confusing. Which of the protons in red is more acidic? More acidic means easier to fall off. Easier to fall off means, are we looking for the weaker bond or the stronger bond? The weaker bond. So we're going to see, well, what's going on here? Well, hydrogen and oxygen. Hydrogen and oxygen, that's the same. The next atom over is carbon. This one is also carbon. Nothing is different so far. Well, what's bonded to the carbon? This one has an oxygen. This one just has hydrogens. This oxygen is going to pull electrons towards itself. This oxygen was already pulling electrons from hydrogen, and now this guy is down the line a little bit, but he's still going to help pull things over. That makes this bond weaker, and this one acts as an acid. This is actually not an acid at all. This particular topic is something that will come up in organic chemistry. So if you're going to take OChem, this would be good to get a handle on. It'll make OChem easier.
So is it more so the easier the hydrogen bond breaks, the
Stronger the
and
acid.
the more acidic?
Yeah. Stronger acid, more acidic, means that it's easier to take that hydrogen off. In a strong acid, the hydrogen, you could think of it as just like voluntarily leaving. It's just like, yeah, this isn't a great situation. I'm going to go right on a water molecule. Right? I'm just really not interacting with my acid, anion at all. So understanding the whole pulling of electrons business and size and everything is good. But this is another way to be able to predict what's going on, to remember the direction of patterns. Oops, not like that. So these are the halogens in the periodic table, right? I told you to memorize the strong acids. Which of these are strong? The bottom three, right? So we can just memorize that. We can memorize 6 things. This whole stronger, weaker business, as it gets mixed up real fast. So these are the strong ones, and this is the weak one. Well, what's different here? Fluorine is smaller, can get closer to the hydrogen, and so this bond is stronger because as you get larger in size, the bonds get weaker. So you can use your memorization of which is strong and which is weak to help you remember that pattern. Because then if I said, well, H2S and H2TE, which acid is stronger? It would be the HTE because Te is larger than sulfur. Tellurium is larger than sulfur, which tells me that the bond with hydrogen is weaker. Weaker bond, easier to lose the proton, stronger acid. And then the bit about the oxygens. So there's 4 related oxyacids, right? Are any of those strong acids? This is strong. I should just circle these. Those are strong. So we identify that as strong because I told you to memorize it, right? Okay, so here, what's the pattern? The one with the most oxygens is the strongest. So it must get weaker as you go to fewer oxygens. So then if we say, well, H2, well, that's not a good, let's do, selenium. Let's do H2SeO4, selenic acid.
So that means with less oxygen is going to be a weaker acid.
Weaker acid. Yeah. So these 2 acids, which acid is stronger? The one with the 4 oxygens. Because we can figure this pattern out from memorizing which is the strong one. That's actually how I remember it. And I use that to trigger my memory so I can explain the reasoning behind it. Any questions?